Okay, so yesterday in the session, we're talking about how Mr. Rabelais wanted you to convert your networks before you did the problems, that would make it easier. And I wasn't quite sure what y'all were talking about, and then someone pointed out to me to look at the examples, and now I see what it was that he was talking about. So what I'm going to do is I'm going to walk y'all through this example, which is the one that he posted, and then after that we're going to work one so this is the one that he posted, but we're just going to work it ourselves, and then we'll do one on our own that's slightly different from this, and we'll see how to make it work. And I might do something else in between, I'm not sure. But here is what we're talking about. So it says apply the necessary transformation in order to use single phase equivalency. Well, and yes, that makes sense. So that is what we're going to do, and it does make things easier. So here we have the transformations that we would make. So we have that V12, it's given equals 440 angle 0 degrees. So notice that we have here that V delta S is given as the square root of 3 VYS. And so we're going to get this VYS. So so V delta S is 440 equals square root of 3 VYS. So VYS is 440 over the square root of 3, which is 254. And what is that? Volts, that's volts RMS. And now notice that let's see, how do we have it listed here? So what we're going to do, I'm going to just kind of modify these formulas a little bit, so we can say V1 equals V12 square root of 3 V1. Let's see, how do I want to write this? Square root of 3 V1 angle 30 degrees equals V12. Square root of 3 V2 angle negative 90 degrees equals V23, and square root of 3 V3 angle 150 degrees equals V31. And so we have the magnitude. So if I wanted to get an expression for V1, I could say V1 equals V12 over the square root of 3, and then whatever my angle was before, I want to subtract 30 degrees from it. I don't know how to write that. Just put minus 30 degrees, because here we are starting from 0 degrees. So V1 is going to equal 254 angle negative 30 degrees. And then V2, this is balanced, so it will also be 254, and it'll be 120 less than that, so it'll be minus 150 degrees. And then V3 will be 240 less than 30, or 120 more, and so that would be angle 90 degrees. So, summary, all I did there was whatever V12 was, I divided it by square root of 3, and then I took the angle and I subtracted 30 degrees from it, and then I went in positive phase sequence. So this is what I'm going to use for my single line equivalences there. Now, in the problem we're given that z delta is 6 minus j2 omega. No, 6 minus j2, not omega, 6 minus j2 ohms. And we want to convert that to the single phase equivalency, and that's equivalent to saying what the y would be. And so the equivalent is going to be, so the single phase equivalent, and so I'll just write it with a y because I'm not sure a better way to write it would be to divide it by 3. So to take your impedance to go from delta to y, or to a single phase, we divide z by 3. Now we want to look at a KVL. So for our single phase equivalency, we're going to have the voltage that we got right here, and then we have the impedance for the line, and then we'll also have the impedance on the load. So our single phase equivalency will have our voltage, we'll have Z line, and we'll have Z load. So here, that would be, if I'm looking at V1, that would be 254 angle negative 30 degrees. And the line we don't have to do anything to that, because that impedance is given right here, and that impedance goes with each individual voltage. Hey kitty, don't do that. Anytime I'm like recording or talking to someone on Zoom, my cat decides that he needs to come up here and shred the papers. So he's shredding papers. Clint, don't do that. Hold on. Alright. So this would be the line impedance was 0.2 plus J1. And the load converted to single phase we got was 2 minus J2 thirds. So now it is easy to get the line current because we just have a simple circuit right here. So the line current, so I line 1 is going to equal 254 angle negative 30 degrees over 0.2 plus J1 plus 2 minus J2 thirds. 254 angle negative 30 degrees over 2.2 minus J1 third. And I don't get exactly the right answer. Why is that? Is that because 1 minus 2/3 is plus 1/3? It is. And so that gives me 114 angle negative 38.6. That's a current, so that would be amps. Once I know that, I don't have to do the other calculations because I know what they're going to be. If I can add and subtract 120 degrees, which is far from a given. So line 2, it's balanced, it'll have the same magnitude, but it will have 120 degrees less, which would be minus 158.6 degrees, and line 3 will be 100 and, was that 113 or 114? I think I copied it wrong. And then line 3 will be 120 degrees more, which would make it angle 81.4 degrees. Now, for a Y configuration, which is what our single phase equivalency is like, you have A and neutral, and so you would have the voltage between A and neutral, and we know that the current in a Y configuration is the same as the line current. And so if I'm looking at a single phase in the load, then I can say that VAN, for instance, equals I line 1 times Z load, which would be now we would use what we just computed, 114 angle negative 38.6 degrees, and Z load we had is J2 minus J2 thirds. And not getting what I thought I would get. Oh, I need to convert to polar. There we go. 240.6 angle negative 57 degrees. VAN, so that tells us that the BN would be 240.6, and then subtract 120 degrees, negative 177 degrees. This is VRMS, and BCN would equal that, and then add 120 degrees, which gets 63 degrees, the RMS. But we want to get VAB, because this number that we have right here would be a single phase equivalent, but we actually want the answer for our delta configuration. And so if we go back to where we started, right here, to get our conversion between our single phase equivalent and our delta configuration, use these formulas. So it will be d AB will equal, write it the same way I have it here. We need to add 30 to the angle, and we need to multiply it by the square root of 3 to get the delta equivalent. So just remember, we're going from our y to our delta, and delta equals y times square root of 3 delta angle equals y plus 30 degrees. And when we went the other way, y equals delta divided by square root of 3, and y angle equals delta minus 30 degrees. And it's the same when you're doing the single phase equivalency. It's equivalent to going to the y, which is where the discussion came from yesterday. And so I'll have 240.6 divided by, multiplied by the square root of 3. And I'll take my angle, which was negative 57 degrees, and I'll add 30 to it. So that is now 417, and I had negative 57, and that gets me negative 27. So my other voltages will have the same magnitude, and they'll be off by 120 degrees, so this will be negative 147 degrees volts RMS. And then if I added 120, I'd get 93 degrees volts RMS.